Mr. Carroll here with a tutorial on how to solve a complex series and parallel circuit that you see here. You have a parallel system here, a parallel system here, and then you have some series elements contained within that. And so the order in which you do things becomes very helpful, because one of the first things that you want to do is find the total resistance in the circuit. That means you have to have the resistance of the circuit. This DC source here is going to be looking down this wire, and it really only sees one resistance. And so we have to get to that point. So the question is, how do we do that? I would recommend getting rid of this parallel system that's right here. You use your parallel resistance formula, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. You'll notice that these things are labeled. And so if we do that, we can actually create a single resistor. It has a resistance of 23.08 ohms, and I've labeled it R9. And that's so that you can keep track of all the pieces. R9 does not exist in the original formula. R9 is a piece that we have calculated for this. Now, if you take a look, these two are now in series. So I can actually take those and put those together and get R10, which gives me 143.08 ohms. Now I take a look at this piece right here, and I have a parallel system, and I can make it R11, and using my parallel function, 21.82 ohms. Now, take a look. Now I have these two in parallel. Both of these are the two parallel systems that we've had with that little one down here that was in series. And if I redo those, I can actually eliminate this and turn into R12 at 18.93 ohms. Now, I have a simple circuit with three series resistors, and if I put those together, I get a final tally of 193.93 ohms, R13. From this, I can calculate the current in the system, the power consumed by the system. But then I have to go back, and once I know the current, I can come back and I can find, since I know the current in the entire circuit, I can find the current in this. And because of that, I can find the voltage drop, and I can find the power. I now know the current in this. I now know the voltage drop in this, and the power in this. Same with R8 down here. So that means R1 and R8 are finished. R12 is a collection of everything that's to the right of this. So I know my voltage drop across from here to here is constant. So when I do this, I know that my voltage going across this resistor, which was R11, is the same as the voltage across this one. I can find the current flowing through here and the current flowing through here. Because of that, I can find the power consumed. But remember, R11 and R10 are intermediary resistors. So R11 can actually be put back into its original form. Since I know the voltage and the current that's coming down this wire, I can figure out the voltage drop here, the voltage drop here, which is the original voltage that sits across this, and then I can find the current. And when I can find the current and I know the voltage, I have the power that is consumed in each of these. Now I go over here and I can take that same concept, but these are in series. So now I can find the voltage drop in this one, the voltage drop in this one. And then guess what? If I know the voltage drop across here, I now know the voltage across each of these. And with that, I can find the current, because if I know the voltage drop and the resistance, I can find the current. Now this is fairly complex and I've gone through it very fast. I do recommend you go back and look at this video and take each piece and see if you can calculate it. I hope this has been helpful.